recording. All right. So today we will get into a new lesson number 4. But before we get into that, any question related to the previous lesson about the n-gram model?
លោកគ្រូជួយឲ្យ example មួយតាក់ទងជាមួយនឹង exercise 3.3 ខ្ញុំធ្វើឲ្យតែខ្លាចខុសប្រហែលជាធ្វើខុស
Okay. So I will open. So I will share my screen. P here. All right.
Lúc khổ sum mới lúc khổ.
Bạn.
Đôi lúc khổ đã làm hại thôi chứ lúc thôi dân miên mối là cái này dân apply smoothing mỗi tiết apply smoothing hay dùng môi nè nhưng plate một bạn đây là khổ tả vì nó dân việc lẽ cái này sầm khăn việc khóc này mới là khổ còn bây giờ việc khóc này mới là khổ pin
និយាយទៅតើតើជាមួយនឹង smoothing ហើយនឹងធ្វើ interpolation ហ្នឹងគឺសម្រាប់ solve នៅពេលណាដែល bigram probability របស់យើងគឺស្មើ0 អញ្ចឹងពេលដែលបើសិនជាយើងរកតែធ្វើតែ estimate likelihood by កណនី probability វាដល់ប្រើ smoothing អត់ប្រើអីទេយើងឃើញនៅក្នុង example previous example យើងឃើញថាយើងមានbigram ដែល probability វាស្មើ0ហ្នឹងច្រើនបើតែ count វាស្មើ0នាំឲ្យ probability វាក៏ស្មើ0ដែរមិនចឹងតែវាមានច្រើនអញ្ចឹងក្នុងករណីហ្នឹងបើសិនជាស្មើ0ពេលដែលយើងចង់កណនី perplexity អីដូចតែនៅក្នុង sentence របស់យើងអត់មានវាមានbigram ដែលមាន0 probability ហ្នឹងអញ្ចឹងដល់ពេលយើងកណនី perplexity ទៅគឺអត់កើតទេគឺវា division by 0 ចឹងហើយបានយើង apply smoothing យើង apply interpolation មាន back off មានអីហ្នឹងដើម្បី solve problem ថាដែល bigram ដែលមាន 0 probability ហ្នឹង
បានលោកគ្រូប៉ុន្តែខ្ញុំចង់ដឹងពីរហ្នឹងវាខុសគ្នាមិនលោកគ្រូinterpolation មួយ interpolation នេះជាមួយ smoothing ហ្នឹងលោកគ្រូតែយើងគួរប្រើឧទាហរណ៍បើចេញឧទាហរណ៍បើយើងធ្វើទៅតែយើងគួរយកអាណាមក apply ដើម្បីឲ្យវាបាន result perform ល្អអញ្ចឹងលោកគ្រូ
អាហ្នឹងអត់អាចនិយាយបានទេអាហ្នឹងវា depends ទៅលើ corpus របស់យើងហ្នឹងអញ្ចឹងហើយជាទូទៅនៅពេលដែលយើងធ្វើ experimentation គឺជាទូទៅយើងត្រូវមាន training corpus ហើយបន្តមកយើងត្រូវមានគេថា validation corpus មួយទៀតអញ្ចឹងទៅយើងសាក apply ពី3 approach ហ្នឹងមកហើយយើងសាកលបង evaluate ទៅលើយក training set យកមក train ហើយយើងសាកលបង evaluate ទៅលើ validation corpus នោះហើយបន្តមកយើងមើលresult វាមកយើងអាចយក perplexity មកធ្វើជា evaluation metric ហើយយើងមើលអាណាដែល produce result ល្អជាងគេអាហ្នឹងគឺ approach ហ្នឹងដែលត្រូវជាមួយនឹង corpus របស់យើង
បានគ្រូតាន់លោកគ្រូអរគុណលោកគ្រូ
Okay, so let me share my screen. All right, so yes, so we have exercise 3.2. So for 3.2, everyone is okay with that, right? It is okay for everyone. It is to apply Laplace smoothing or advanced smoothing. For example, if we want to compute the probability of this word do given start token, or probably let's try to do this one. Probability of I given do. So let's look at the corpus. Okay, so here is our corpus. Okay, so here is our corpus, and we would like to compute probability of I given do. Okay, so if it is not Laplace smoothing, if we compute directly, this is equal to what? This is equal to count of
do
I divided by count of do, right? So do I, how many do I? You have one here. Over the count of do, how many do's? So we have two do's. So it is equal to 0.5. This is the probability without applying any smoothing. So now let's try to do, let's try to apply smoothing. So P at 1 of I given do is equal to, we have to increase the number of count by 1, right? So here, 1 plus 1. And for the lower part, 2 plus how many?
the word data.
Powerful.
Yes, the number of vocabulary in our corpus. So we have 1, 2, 7, right? Last time it is 7. So yeah, 7. So it is 2 over 9. Okay. Yeah. So this is Laplace smoothing. And for exercise 3.3, we apply, we do not apply Laplace smoothing anymore. This time we apply at k, and k is equal to 0.1. So if we would like to compute p, so p at k of do of I given do, so it is equal to 1 over 2. This time we plus k, right? So k is 0.1, so we should plus 0.1 divided by k multiplied by v. So 0.1 multiplied by 7 equal 1.1 over 2.7. Okay, so this is the probability of P at K. And for 3.3, we have to do interpolation as well. So we have to compute the bigram as well, because in order to compute the probability of this one, we have to use the probability of, no, not bigram, unigram as well. So let's say that if we would like to compute P hat of I given do, so this one we compute already. What about this one?
Need to find again and follow the at k.
Yes. So P at K of only, this is a unigram. So the word that we are looking for is I, right? So it is equal to count of the word I, right? Divided by how many?
Divided by 7.
No, not really 7.
7 and plus 0.1 multiple that with 7, right?
It is not divided by the number of words in the vocabulary. This is divided by the total number. Yes, total number of words in the token in the corpus.
27 teacher.
Yeah, so you have to count the total number or the total number of tokens in the corpus. Okay, so 1, 2, 3, 4, 5. So 27, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But yes, 27. So it should be divided by 27. Okay, so untoken. And then we have to apply add k smoothing. So here we plus 1, no, not plus 1, plus 0.1. And for the lower part, plus 0.1 multiplied by, this time the number of vocabulary, the number of words in the vocabulary, so it should be 7. So it is equal to how many I in our corpus?
5.
Yes, so 5.1 over 77.7. Right? So this is the property of the unigram, and then we can use this formula in order to do the interpolation. So this number multiplied by 0.25, and this number multiplied by 0.75, and then we do the sum, and we will obtain the final probability p hat.
Teacher ខ្ញុំកន្លែង probab នៃ PW ហ្នឹងយើងត្រូវ follow តាមរូបមន្ត P and K ដែរមែនទេព្រោះខ្ញុំឃើញរូបមន្តហ្នឹងទាល់តែមានអាលក្ខណៈ slash ហើយ double ដូចជារូបមន្តមានslash នៅកណ្ដាលហើយ W I ដក 1 អញ្ចឹងដល់ពេលអញ្ចឹងទៅអាកន្លែងហ្នឹងខ្ញុំអត់បានធ្វើដូចជាលក្ខណៈយក C ហ្នឹង C នៃ I បូក 0.1 អញ្ចឹងគឺខ្ញុំយក probab direct ហ្មងគឺ CI នៅលើ 27
ហ្នឹងហើយអត់អីកន្លែងហ្នឹងយើងអាច approximate មកអញ្ចឹងក៏បានដែរព្រោះឲ្យវា doesn't change much actually
លោកគ្រូខ្ញុំចែកខុសអាកន្លែង27ហ្នឹងខ្ញុំយកតែ7ខ្ញុំយក word token វិញ
ហ្នឹងហើយអាហ្នឹងមិនជា word token ទេ unigram គឺចំនួននៃ word ចំនួននៃ unigram ហ្នឹងចែកទៅលើចំនួន token សរុបនៃ corpus របស់យើងមិនចំនួននៃ token types ណាចំនួននៃ tokens បើសិនជាយើងចែកទៅនឹង vocabulary ចាំបានថាគ្រប់ unigram ទាំងអស់ probability វាស្មើគ្នាមិនអញ្ចឹងវាអត់ make sense អញ្ចឹងឯង Okay, yes, you can ask the question.
លោកគ្រូពេលដែលខ្ញុំចែកក្នុងអ៊ីនធឺណិតហ្នឹងពេលហ្នឹងពេលខ្លះគេរាប់ទាំង whole sentence ពេលខ្លះគេចោលអាកន្លែង A ពីមុខអាហ្នឹងបើយើងចោលបានអត់ក៏យើងត្រូវទៅរក whole sentence មក
we is the vocabulary. What do you mean the whole sentence?
យើងត្រូវរាប់គ្រប់ពាក្យនៅក្នុង sentence ទាំងអស់ហ្នឹងហ្មងឬក៏យើងអាចចោល A ដោយសារតែពេលខ្ញុំឆែកក្នុងអ៊ីនធឺណិតទៅគេដាក់ចោល A ក៏បានរាប់កន្លែង A ហ្នឹងក៏បាន A កន្លែងដើមក្បាល sentence នេះលោកគ្រូ
ហ្នឹងហើយអាហ្នឹងវាតែថាយើងដោយសារកន្លែងនេះ corpus យើងតូចអញ្ចឹងយើងហ្នឹងហើយយើងអាច count ទាំងអស់ទៅពីព្រោះមែនតើពេលដែល corpus របស់យើងធំអញ្ចឹងអា vocabulary របស់យើងហ្នឹងក៏ច្រើនដែរចុះជួនកាលអា token ខ្លះ ខ្លះដែលវាអត់សំខាន់ណាឧទាហរណ៍ថាដូចតកតងជាមួយនឹង preposition ដូចជាអីហ្នឹងអានោះជួនកាលក៏គេអត់ count ដែរអញ្ចឹងមែនតើមិនមែនតើធ្វើមក start token ហើយនឹង end token ហ្នឹងទេចង់និយាយថាពាក្យមួយចំនួនទៀតដែលវាអត់សូវសំខាន់នៅក្នុង ដែលបញ្ជាក់ពី meaning នៅក្នុង text corpus របស់យើងហ្នឹងអាហ្នឹងក៏គេ ignore ចោលដែរឬមួយក៏គេអាច group វាចូលគ្នាឲ្យទៅជា token ឯផ្សេងមួយទៀតអញ្ចឹងទៅ
So លោកគ្រូខ្ញុំសុំសួរមួយទៀតកន្លែងតំណឹងបើយើងរកអា perplexity យើងយកប្របាប់របស់ SK ឬក៏យើងយកប្របាប់របស់អា linear interpolation ហ្នឹង
យកទាំងពីរហ្នឹង
អញ្ចឹងមានន័យថាយើងរក perplexity ពីរដងទៀតអានៅលំហាត់ហ្នឹង
No so what so in order to compute the perplexity you can see the formula of how we can compute the perplexity where is it okay right here so we have to compute in order to compute perplexity we have to compute the probability of the whole sentence in the test set right and in order to compute the probability of the whole sentence you can see we have to do a lot of products of the probability of bigram if we use a bigram model. So here in order to compute this, you can use a p-hat. Okay. So let's say like yes, let's say this one, right? So in order to compute the probability is pp is equal to a root the 1 2 3 4 5 the fifth root of 1 over p of the sentence, right? As do Sam I like. Okay, so in order to compute this, it is equal to p of do given s multiplied by p of Sam given do multiply of p multiply with the p of I given Sam and finally multiply with p of like given I. Right? Yeah. And in order to compute the probability of the bigram of this one of each of these probability is computed with the interpolation and the add smoothing. It means that you have to compute p hat for each of the probability. For 3.3. Okay, so the perplexity in 2 and 3.2 and in 3.3 they are different, so that you can compare. Like if you use just Laplace smoothing, what is the perplexity of this sentence? And if you apply add case smoothing and also the interpolation technique, what is the perplexity of this sentence? And then you can compare which one is better.
លោកគឺសុំសួរមួយទៀតអារឹសទី5ហ្នឹងយើងរាប់ចំនួនដែលនៅក្នុង A នឹងមានចំនួនប៉ុន្មានតើលោកគ្រូថាប៉ុណ្ណឹង
The number of tokens in the test set in the test corpus.
លោកគ្រូចោះចាក់ខាងលើដូ I ហ្នឹងឥឡូវស្រេចកូនលេខ2មែនលោកគ្រូ
Sorry. What is the question again?
ដូចឥឡូវខាងលើហ្នឹងយើងហៅរកបាបនៃដូ I លើអីហ្នឹងឥឡូវយើងស្រេចកូនរៀមហ្មងលោកគ្រូ
ở tại khang lớn này ở vài con này khang lớn này pi tên cái gì nè đây đại nhóm ban mention tăng pi khang đam này đây Marian nâng chứ chỉ tu tới pe là dân vậy pi language model cứ dân vậy pi caro probability anh mình pi nhá pi mỗi cứ the upcoming word what is the probability of the upcoming word nè này hết cứ the upcoming word chứ bài tha bà sân chỉ là lời nó sentence bao giờ là lời nó tiện trong khỏi cái cứ để khẳng lại đi bà sân chỉ tiện trong khỏi cái đủ cho xây máu tao mất đủ chắc số ta tiện và to bị đủ nó cua ta chỉ ấy cái này ok p đại I given đủ probability đại tiện và to bị đủ nó cứ chỉ the word I nó mà nó mùiเราไปข้างโคมนี้เว้นคือยัง compute the probability of the whole sentence ตอนในถ้าภาษาจะ sentence ยังจังตา probability เป็นประมาณได้วิจี sentence ประกอบในขนม corpus ไปอย่างนั้นจังอ่ะปีนั้นเซ็งกันเดียวเราไปยังตระการแก้แต่เนี้ย perplexity คือยังแก้แต่เนี้ย perplexity สิ่งที่ปรากฏเนี่ยข้างเลยได้ยังเอาเนี่ยถ่ายการแก้แต่เนี้ย perplexity เดียว
จังเวลาท่าperfectity นั่งยังโหดในក្នុង sentence ได้ไหม
นั่นไงบางทีถ้า perfectity นี่คือจะรวมวอร์มวยนำไป evaluate ถ้าตาเป็นอย่างประกาศจี language model ให้ยัง generate จริงจี sentence นั่งถ้า sentence นั่งเวียใครถ้า resemble the real sentence มีในขนม corpus ไปอย่างนั้น
นั่นแหละผม
นั่นเลยจัง complexity นั่นเป็นปัจจัยជាមួយនឹង probability បានន័យថាបើសិនជាតួលេខកាន់តែតូចអានោះបានថា model language model របស់យើងហ្នឹងគឺកាន់តែល្អអញ្ចឹងយើងអាចយកអាហ្នឹងយកមក compare គ្នាបានអញ្ចឹងបានដូច exercise 3.2 និង 3.3 នេះយើងប្រើ language model ពីរផ្សេងគ្នាតែអានេះប្រើ language model bigram ប៉ុន្តែ apply Laplace smoothing ដល់ពេល 3.3 នេះ bigram ដែរប៉ុន្តែយើង apply SK វិញហើយបន្ទាប់មកយើង apply interpolation technique ទៀតអញ្ចឹងវាជាពីរ language model ផ្សេងគ្នាអញ្ចឹងបើសិនជា language model របស់យើងសាកល្បងកណនី probability នេះមើលហើយនឹងនេះដែរហើយយើងកណនី complexity ទៅតើមួយណាដែលល្អជាងអូខេOkay, any other questions? Okay អញ្ចឹងអត់អីទាំងអស់គ្នាអាចអញ្ចឹងខ្ញុំអាចចូលមេរៀនថ្មី
ធ្វើ assignment ខុសលោកគ្រូ
Okay. All right. So yes, if there's no question, we can move on to the next lesson, which is about text classification. Okay. All right. Yes. So, okay. Text classification. So yes. So when we talk about text classification, here are some applications about text classification. So when we talk about text classification, the input is a text, and we would like to classify the text into different categories. For example, like Here you can see some examples like spam detections. So spam detection, do you know spam? Spam email. Okay, so the input is an email, and we would like to identify if the email is a spam or not. Okay, so we have only two classes for this one. Right? Two classes. Spam. Not sure what happened with my PowerPoint. Okay, is it spam or no spam? Or we can just say yes or no. Right? One PowerPoint or data set we just okay, yes or no. So we have only two classes, and this one it is called binary classification. Writer identification. Sometimes when we look at a text, we can identify the author of that text. It can be like a piece of literature, and just by looking at the how the article or the text is written, we can identify the author of the text. So the class here, classification here, the number of classes is the number of authors that we can identify. Classification of a news article. Okay, so we can have like many categories of news article, and by inputting the article into our system, the system can like analyze and identify which category does that article belong to. Okay, movie review. Okay, some comments or some feedback on a movie from the user. We can also analyze the text and then output if the review is positive or negative. Also sentiment analysis. For example, if you look at a status or a comment on Facebook, you can create a system in order to analyze the text and try to find out what is the sentiment or what is the emotion of the writer. Right? Is the start. Does the starter show I mean that if we look at the status, the Facebook status, if we can know like if the writer is angry, is happy, is sad. Okay, so different types of emotions, we can call it like the classes. Okay, yeah. So here are some examples that we can do for text classification. Okay, yeah. So yeah, in order to build a text classification model, so I think we should know about classification in general first. And before we get into classification, let's talk about linear regression. Have you ever heard about linear regression? Are you familiar with the term linear regression? នៅម៉ោង AI មានរៀនដល់ហ្នឹងនៅ linear regression អូខេ
Đôi chia chia là nào
Okay ចឹងបានន័យថាអត់ familiar ជាមួយនឹង linear regression ទេ
bạn là cổ để trả hiện algorithm đối line về được ấy chứ
Okay. Yes, for linear regression, it is a model that we take some input and we try to predict continuous value output. Like in this example, the input is land area. We would like to build a system to predict the price of a land. And the input is the area of the land. Okay, and the output is the price. So you can see here the price is a continuous value. Okay. Yes, and linear regression, it is part of supervised learning. You know the difference between supervised learning and unsupervised learning, right? So here it is like the basic idea of machine learning. So we have supervised learning and unsupervised learning. When we talk about supervised learning, it means that we have both in our data set, we have both the input and the output. And we would like to build a system in order to predict the output. And in order for the system to be able to do that, we have to train the system, right? By training the system, we have to provide both the input and the real output to the system for it to learn. So it is called supervised learning. And for unsupervised learning, it means that we do not, in our data set, we have only the input. We do not have the output. We do not know what is the output. So for unsupervised learning, usually we try to find the pattern, the structure or the organization of the data. Okay. An example of unsupervised learning can be about clustering algorithm. So we have a lot of data. We can group the data into different clusters. Okay, so this is an example of unsupervised learning. But for linear regression, it is one of supervised learning. So you can see that in our data set, we have to collect both the input and the output. And our system will try to predict the output. Okay, yeah. And for linear regression in particular, the output is continuous value. Okay, yeah. So, yeah. So like I mentioned, for supervised learning and also for unsupervised learning, we have to have training data. We have to collect a lot of data in order to train our system, our model. So here are some notations that we will use throughout this lesson. So yes, let's denote M to be the number of training examples in our data set. X is the input and Y is the output. Okay. Yes, and if we write X, Y inside the parentheses like this, it is to represent one training example. Okay, so this is an input and output pair of one example. And you can see we can also write the superscript I here to denote what is like the ith example in our data set. Okay, so actually yes, like for example this one. This one we can just write x1 y1. Okay, and this one x2 y2. Okay, so the number in the parentheses in the superscript here represent the order or the position of the example in our data set. And here sometimes we start from 0. If like yes, For example, in Python, the starting index is 0, so you can just start. The first example is h0. Okay, yeah. So these are just some notations that we will use. Okay, yeah. So here you can see this. This is the data visualized in a graph, and then we can also present it in a table like this. Okay, so we have two columns. The first column is the input, and the second column is the output. And each row represents each example in our data set. Okay, next. Model representation. Okay, so here you see the training set, and then we have to find an algorithm in order to use this training set in order to train or for our system, for our model to learn. And here we have to define a hypothesis as well. So hypothesis here, it is the representation of our model. We call it a hypothesis. So you can consider hypothesis as a function, and the input into the function is our input x, and we would like to try to output or try to return an estimated value, an estimated value, right? So you remember we have collected in our data set, we have collected the x and also the real output. So y here is the real output that we have collected. And z here, you see that I use a different name, because this one is not really y. This is the estimated value predicted by our hypothesis. And if our hypothesis is good, z is very similar or like identical to y. If we can make z identical to y, it means that our hypothesis is good or our model is good. Okay, yeah. Oh, for linear regression, the hypothesis is like this. You see? This is the line equation, right? Do you remember? So this is our hypothesis, So we have only one variable, which is the input x, and we have two parameters here, okay, a and b. So what does it mean? So it means that we would like to try to find a line to fit this data. Probably it can be something like this, right? So in order to draw this line, we have to know these two parameters, a and b. That is why this one is our hypothesis, and the name linear regression, right? Because it is a line. So the question is, so now we have the training set, the training data. We have the hypothesis, we have our parameters, we have two parameters A and B. So the question is, how can we know the value of A and B so that we can find a good line in order to fit our data? That is why we have to apply our learning algorithm. Okay, and we have a lot of learning algorithms. For this lesson, we will use one learning algorithm called gradient descent. Okay, we will see in detail in the next few slides. Okay. So let's get back to the cost function. So when we so let's look at the hypothesis first. So you can see we have to look for like a good set of parameters A and B. So if the value of A and B change, we will obtain different lines as well. So for example, if A is equal to 1 and B is equal to 0, our line is like this. If A is 0, B 1.5, our line is like this instead. right? Different sets of values of A and B, different line. So we have to find the one that is the most appropriate, the best for our for fitting our training data set. Okay, so here, in order to find A and B, we have to define a cost function. Okay, so when we talk about a cost function, is the way in order to compare between the predicted value from our model with the real output. Okay, so again, the value predicted from our model or from our hypothesis, it is Z, right? And the real output is Y. So we have to compare between the two. And we want both of them to be very similar, or very, if it can be exactly the same, it means that our model is perfect. But usually in practice, these two values cannot be exactly the same. It can be similar. Okay, so we want Z to be as similar as possible to Y. That is why we have to define the cost function. So the cost function, if Z is very similar to Y, so the cost will be very small, close to 0. So usually a cost function will return a cost, and the cost is a value cannot be negative. Usually it is from 0 up until infinity, and we want the cost to be as small as possible. It means that we want the cost to be close to 0. Okay, yeah. And for linear regression, we can use a cost function called square error function. Okay, so for square error function, we can just, in order to compare these two values, we can just use this formula. You see? So here it is Z, right? It is Z. So we can just do find the difference between Z and Y, and then to the power of 2. Why we have to apply square? Anyone? So we would like to find the difference between Z and Y. And then we use this formula. And also, if we would like to find the difference, we can just do the subtraction, right? So why do we apply square? Because?
I think maybe because we don't want to get it negative.
Yes, we do not want to get a negative value, because the difference can only be 0 or a positive value, right? Like, let's say if Y is equal to like 100, and what we predict is, let's say, 80. Okay, so if we do the subtraction, we will obtain like minus 20. And if we have one more like a different model, and the predicted output is, let's say, 110. Okay, so when you find the difference, it is 10, right? If you do the subtraction. So actually, you can see that this one is minus 20 and this one is 10. We don't want that. We just want the distance between Z and Y. So we can just square it, and we will obtain just the positive value. We can also use the absolute value like this. You can see the absolute value. But actually, you will see that in our learning algorithm, the gradient descent, we have to do derivatives. So it is better to, it is much simpler to differentiate to find the derivative of something square rather than something after applying the absolute value. Okay, yeah. So yes, in summary, we will use this cost function for our linear regression model. And what about this? The sum or over m, What does it mean? It means that here this term is only the distance for the difference for just one example, right? So in our training set, we have a lot of examples. So the cost is the average of the cost of all examples in our training data set. That is why we have to sum all of the differences together and then divided by m. M is, again, m, our notation, it is the number of examples in our data set. Okay, so sometimes it is called as well mean square error. Okay, mean is average, right? Yeah. So here is our cost function. And in order to find a and b, we have to look for the value of a and b that makes this function as small as possible. Or we can say that we would like to minimize this cost function j. Okay, and you can see the parameter is a and b. We have to look for the value of a and b. We have to look for a and b that makes this j, that makes this cost function very small. Okay, yeah. So yes, now we will get into the gradient descent, which is our learning algorithm. So if we have a sum function j, this is the cost function, and we would like to minimize it, we can do something like this. So this is our parameter. These are our parameters that we want to find. So we have to first initialize the value of a and b of our parameters with any value, with any random value. It doesn't matter. Okay, and then we have to keep changing a and b. We have to update the value of a and b so that the cost function j decreases. And if we do this a lot of time, so we hope that the cost function will decrease to a very small value. And then if it is small enough, we can just stop. And then we will find out the final value of a and b here. Okay, so this is the idea behind gradient descent. Okay, so let's look into that in more detail. You can see here, keep changing a and b. So how can we change a and b? How can we update a and b in order to reduce the value of j? Here we can do the derivatives or partial derivatives because we have multiple parameters, right? So when we do the derivatives of j with respect to a, we call it with a or with b, we call it gradient. Hence the name gradient descent. So this is gradient with respect to a. So we have to do derivatives. We have to differentiate j with respect to a. Okay, yeah, and we have to do this for all of the parameters in our hypothesis or in our model. And then in order to update a and b, we can just use this formula. We will add gradient into our old value of our parameters. Okay, yes. And also we usually also multiply the gradient with this value, alpha here. We call it the learning rate. Okay, in order to understand this, let's try to plot a graph. So let's say that the vertical axis, this is our cost function j. And because we have two parameters, right? Let's look at just one example. Let's just look at one parameter to simplify it. So let's say that we try to find the value of parameter A. Okay, you can see the cost function. The cost function is like this. Okay, so if we plot, we would obtain something like this. Okay, so this is our graph representing J with in function of parameter A. Okay, so in our algorithm, first we have to initialize the value of A with any value, with any random value. Let's say that we initialize A is equal to 1. So 1 is right here. Okay, so we can say that if A is equal to 1, the cost is right here. Okay. Yeah. The cost is here. So when we do the derivative, what does it call? មេគុណប្រាប់ទិស in English. Anyone knows what is មេគុណប្រាប់ទិស in English? មេគុណប្រាប់ទិស of a line. No, what does it call? Slope. Yes. It is a slope of a line, right? So if we have a function like this and then we try to do the derivative, it is a slope of a line touching this curve, right? Right? Yeah. So the line should be something like this. Let me change the color. So here, so we have a line like this. Okay. Again, a line something like this that touch this slope. Okay. Yeah. So you can see that if our line is like this, the slope, is it negative or is it positive?
Positive.
Is it positive or negative?
I still feel positive.
I have something like this and like this. If the line is like this, the slope is it negative or positive?
គ្រូចង់និយាយថាវាទៅពីខាងណាទៅខាងណាមិនថាមើលអត់តមានក្រា slow គ្រូ
ណាខ្ញុំចង់សួរពីមេគុណប្រាប់ទិសទៅសម័យកាលបន្ទាប់យើងអញ្ចឹងតើមេគុណប្រាប់ទិសវាព្រោះអា gradient ហ្នឹងឯងគឺជាមេគុណប្រាប់ទិសនៃបន្ទាប់ហ្នឹង
ច្រឡំហ្នឹងគ្រូអាហ្នឹងវាដូចជា positive គ្រូ
Okay, this one is positive and this one is negative, right?
Yes.
So this one is negative. So you can see that the starting position, the starting value of A is right here, right? And where is the minimum of our function? It should be right here, right? So this is it is where J is the minimum, and the value A that makes J minimum should be right here, right? So you can see that in order to change the value of A from here to here, what can we do? We have to move to the right, right? So we have to add positive value to the initial value of A. That is why you can see that the gradient is negative here. And if you have to move to the right, that is why you can see we add minus gradient, sorry. You see? Minus gradient. So the opposite direction of gradient. Okay? Yeah. So this explains this formula, this expression. Again, like it doesn't matter where we initialize our parameter A. Let's say that if we initialize it right here instead. So let's say that this is 10. Okay. So you can see our cost function is right here. And if we try to find the gradient, it would be positive, right? So you can see here positive, and A is right here, and A should go to the left, should be smaller, right? That is why we minus the gradient. So A should move to the optimal location right here. Okay, that is why the name of this learning algorithm is gradient descent. Okay, descent. So the opposite direction of gradient. And what is the benefit of learning rate? So you can see that we have to update, we have to change the value of A and B. But the question is how big do we have to change it? So the hyperparameter alpha here, it represents like how big do we need to change the value? Do we need to update the value A and B? So if alpha is big, if alpha is big, it means that we have to change a lot as well. So let's say that first our parameter A is here, and then just after one iteration, because alpha is big, we can update it until right here. If our we can call it as well like step. Okay, small this one big step because alpha is big, and if alpha is small, we will update just a little bit, maybe like from here to here. Okay, and you can see after we update our parameter, you can see when we try to find the cost function again, the cost again, you can see that the cost decrease. So after each iteration, this is a loop. Okay, this is a loop. We have to do a lot of iterations. We have to update the parameter like a lot of times. So each time we will update the parameter with some value. So the cost will keep decreasing. Okay, so after we arrive here, you can see that when we arrive here, when we try to find the gradient again, you will see that when we try to update it, the cost will not decrease anymore, or will decrease very little, or sometimes it even increase a little bit, right? So it will fluctuate here, the cost. So we can stop here. It means that we arrive at the optimal location for our parameters. Okay, so to summarize, what is the drawback when alpha is too big? Okay, if alpha is too big, what is the drawback? And when alpha is too small, what is the drawback? Any idea?
I think if alpha is too big, maybe get we might get over the optimal location. Maybe.
Yes, that is correct. So if alpha is too big, it means that our step is very big as well. So sometimes we can go past the optimal location here. Like sometimes I'm until right here. Okay, so we will here instead. And then you can see if we are right here, we have to go back, right? We have to go to the left. So when it is big again, so we have right here. Okay, so you can see that we have to go back and forth, and we will never be able to arrive at the optimal location here because the step is too big. And what is the drawback when alpha is small? It's too small. So when alpha is small, the positive point. No, when alpha is small, it means that I mean the good thing is that we will always make sure that we will always be sure that we will arrive at the optimal location eventually. But what is the drawback if it is too small? We have to do a lot of iterations, right? Because we just update the parameters a little bit. So we have to do a lot of updates. So it means that here is our training, right? That we apply gradient descent because gradient descent is our learning algorithm. So this is called training. So the training time will be very long. You have to do a lot of iterations. So that is the drawback when alpha is too small. So you have to choose a good alpha in order to have a good training for your model. Okay.
Hello, sir. I want to ask that when will we know that we arrive at the optimal point so that we can break the loop?
We can observe the value of J. You will see that at the beginning, J will decrease a lot. And after some iteration, you will see that the decreasing of the J starts to slow down. And at a time, it will stop decreasing. Or it will decrease, but very, very little. And if we see something like this, we can stop the learning algorithm.
Okay, thank you.
Or we can just try, like, for example, like if it takes only 100 iterations for us to reach the optimal location, we can also train, like continue to do the training. The result won't change. Like if we continue to do like 100 more iterations, the result is still the same. Like because J is already at the minimum, so it doesn't decrease anymore. So the update of our parameters will fluctuate. Right? So even though we continue to do the training, it doesn't change much the value of our parameter. So in practice, usually we just try, like let's say we train with 500 iterations. It can take less than 500 iterations to reach the optimal location, but it is okay as well to just train 500 iterations. Do you get my point? កន្លែងហ្នឹងខ្ញុំចង់និយាយថាពេល in practice មែនតើទៅយើងពេលដែលយើង train បានន័យថាយើងអាច train ឲ្យលើសបានវាអត់មានបញ្ហាអីទេបើសិនជាក្នុង model របស់យើងហ្នឹងគឺ100 iteration វាគេថាវា converge ហើយប៉ុន្តែក៏យើងអាច train 200 300 400 500 iteration បន្តទៀតក៏វាបញ្ហាដែរតែពេលដល់វា converge ហើយបានន័យថា parameter របស់យើងហ្នឹងគឺវាឡើង change value much ហើយវា change only a little bit អញ្ចឹងទោះបីជាយើង train បន្តទៅទៀតក៏ដោយក៏វាអត់មានបញ្ហាអីដែរអញ្ចឹង in practice វាច្រើនគេ train ច្រើនតែម្ដងទៅថាគេ train 500 iteration 1000 iteration អីចឹងទៅអញ្ចឹងទោះបីជាវាconverge មុនណាហ្នឹងក៏ដោយក៏អត់បញ្ហាដែរយើងអាចនៅតែដាក់បន្ត train ដល់ចប់1000 iteration ទៅគឺយើងបាន final value យកតែម្ដងOkay. So here is the derivatives of our hypothesis. You remember the hypothesis. So we have a of x is equal to ax plus b, right? And here is our cost function. And when we try to find the derivative of the cost function with respect to a and b, we will obtain something like this. Okay, so here's the gradient with respect to a, and this one is gradient with respect to b. Thế chẳng dân ai xa là bon đây là vềខ្លួនឯងបានចឹងដល់ពេល derivative ហើយវាក៏តែឃើញចឹងដែរណា And again this is partial derivative. It means that for example if we do the partial derivative with respect to a, it means that we consider only a to be the variable. The variables other than a, we consider them to be constant. Oh, okay. Okay, so before we get into the exercise, any question up until now? Okay, a question? Is it clear for everyone? No question?
លោកគ្រូ alpha ហ្នឹងយើង set កន្លែងខ្លួនឯងមែនលោកគ្រូ
Yes, you have to choose the value of alpha by yourself.
តែយើងត្រូវសិក្សាវាថាយើងត្រូវដាក់ប្រមាណដើម្បីឲ្យវា fit នឹង data របស់យើងមែនលោកគ្រូ
Yes. In order to find the value of alpha, you can do a lot of trials and error. Like let's try, and in practice, usually we try with something like 0.1. We start with alpha is equal to 0.1. And then we observe the cost, if it decreases a lot or not, or if it is too big, it means that the cost does not decrease, but it increases. So it means that it can be a sign that tells us that the alpha is too big, the value of alpha is too big. So if we want to increase or decrease the value of alpha, we can do it in the multiple of 10. Okay? So if we find out that 0.1 is too small, we can just multiply it by 10. So we change it to 1 instead. And if 1 is still too small, let's 10. And if 0.1 is too big, we can decrease it. So divide it by 10. So 0.01, something like this. Okay. Yeah. So you can try different values of A in order to see which one is the best for your model, for training your model. Okay. By looking at how the cost changes.
លោកគ្រូចំនួនហ្នឹងវាជា like ចំនួនរបស់ data ត្រូវលោកគ្រូ
Yes, M is the number of examples, the number of data in our training set, in our data set that we use for training the model. Okay. All right. So if there's no more question, we can get into exercise 4.1, the first exercise. So we have our data set here in the table. So we have only 10 examples, which means that M is equal to 10. And we would like to find or to build, to implement a linear regression model that fits this data set. So what can we do? Okay. We can just implement in Python. We just choose Python. So let's try together. Okay, code NLP. Okay, I can just create one more Google Colab, I think. Okay, so let's call it exercise 4.1. Okay, so first let's create our data. So we have X to be an array with 10 elements, 10 examples. Can you help call the value for me?ពួកយើងអាចជួយហៅលេខបន្តិចមកខ្ញុំវាយបញ្ចូលចូលតែម្ដង Anyone?
គ្រូហៅ M មុនមែនលោក
ហៅ X ណា input X column ទី1
អូខេ90 130 210 300
30ហើយអីទៀត
210 300 350 420 408 530 640 710
អស់ហើយណាអូខេហៅ y ម្ដង
7.1 10.9 19.2 28 32.8 39.4 46.1 51 62.2 68.4
Okay, so that is all. So we have the inputs and the outputs, right? So we have two arrays in order to store them. And after that, we have to define our hypothesis. Right, so we can create one function called hypo, or just h, to represent our hypothesis. So the input is xi, right? Only one example. And we have to have two parameters, a and b. For this function, we can just return a multiplied by xi plus b. So this is our hypothesis, right? Yeah. And then we can define one more function as our cost function. So let's call it cost function. So in order to compute cost function, we have to we have to know zi and then yi. Or maybe okay, just or probably we can also input x and y, the whole data set. Okay? So h here is a list, y is also a list. So here we can do something like we have to compute the cost for each example. So let's write something like cost is equal to 0, and then we can just use one loop. Okay, let's also declare variable m to be length of x. So here is we have loop m times in order to compute the cost for each example. And in order to find the cost of example, we can just find the square, right? So it is cost plus equal to y or x. No. We have to find the predictive value. So it is h of xi ab, right? So here is our hypothesis. So it will output the z, right? The predicted output. Then we have to minus y, and then multiply by 2. Not multiply, square to the power of 2. Can we do this in Python? Print 10 square.
Actually, like 2 star and 2. Oh,
No.
we can. 2 star.
We can
two.
use function pound.
We
2
cannot
star,
do this
2.
in 2 star.
Yeah,
Something like this.
you can try 2 star.
Okay, yes, 2 star. Okay. So we can write something like this, to the power of 2, and then we can just return cost divided by m to find the average. Okay, so this is our cost function. And also we would like to find the gradient. First, gradient with respect to A. We can look at the formula in our lecture. Okay, so here's the how we can compute gradient. So for A, you can see that 2 over m, the sum of h of x minus yi multiplied by hi. Okay, so it should be we need, in order to compute the gradient, we need x, y, a and b. This one we also need a and b, right? A, b. And this one we also need a, b, and y. And in order to compute, we can just grad is equal to 0. We compute m again, and here we have to write one loop in order to compute okay, 8 minus y multiplied okay, so 8 of x, so here 8 minus yi, right? And then everything multiplied with h of I, x of I. Right? Okay, yeah. And then we return grad multiplied by 2 divided by m. Yes, and the same thing, similar thing for gradient with respect to b. Okay, here you can see we do not have to multiply with hi, so we can just remove this. And that's it for grad b. Okay, so I think we have everything that we need, and then we can just do the training. So first we have to initialize a and b with some random value, right? So let's say a is equal to like 10 and b is equal to 20, just any value, it doesn't matter. And then we have to get into a loop. So let's do it 100 iterations. Okay, yeah. And then we have to compute the gradient. We have already defined the two functions to compute the gradient. So grad maybe GA is equal to grad A X A B Y, right? And gradient of B is equal to grad B X A B Y. After we find out the gradient, we can update our parameters. So A plus minus alpha multiplied with gradient, and B plus equal minus alpha multiplied by GB. Okay, we have to define alpha. So let's say alpha is equal to 0.1. Let's start with this. Okay, yeah. And so we would like to know, we would like to observe the cost, right? To see if it decreases or not. So let's compute the cost as well. So I will compute the cost here is equal to cost function X, A, B, and Y, right? And then I will try to print out the value of cost. So iteration, I will print out the iteration and then the cost. And then the value of A. And the value of B. Okay, and that's it. So here it will be iteration, cost, A and B. Okay, and that's it. So this is our learning algorithm. This is our training in this loop right here. And we will do that 100 iterations, 100 times. Okay, so let's try to run it. Hope there will be no error.
You have 4 parameters.
Okay, cost function, we need Y as well. All right, so actually it runs, but you can see that, you can see the cost at iteration 0, the cost is something like some million. And then after we update the parameters, you can see the cost, it doesn't decrease, but it increases, right? So what happens here? So what can be the cost? And what can we do in order to make it right? Why does the cost increase?
Like it's not fit to our data, the line or something, I'm not sure.
You can see right here, just like like you remember we talked about like different value of alpha. If alpha is too big, it means that it will go past the local position, and then you can see that the cost will increase. So here it means that the learning rate here is too big. So let's try to make it smaller. So let's use 0.01 instead and try to run again. It is still too big, you see? So even smaller, still too big, even smaller. Okay, still too big. Okay, so just you can see that right now it increases, but it does not it increase as much as before. So it means that we go in the right direction. We can continue to decrease the learning rate. Okay, so right now you can see that the cost now decreases. Okay, so yes, we can use this learning rate for our training. And you can see that start from here, and after iteration number 20, you can see that the cost decreases, but it doesn't decrease much anymore. Actually, just by observing this outcome, you can see that we can just stop the training with just 20 iterations, and it would be fine. Okay. Okay. So what can we do in order to see if our model is good or not? We can just compare. So after training, I can also create one more block here in order to evaluate. So we can just compare what our model predicts and what the real output is. Okay. So let's say m is equal to length of x, and for I in range m, we can first the value, so I can say z, right? And then compare with y. So here z, it is our hypothesis, so x a, x I a b, and for y it is yi. So let's try to run this one. Okay. So here is the real output, and here is the what our model predicts. Okay, so what do you think about this result? Not very good, right?
Yes.
You can see that it learns, but the output from our model is not very good. Okay. Actually, the problem is for this one is about the learning rate again, because here we have two parameters, right? A and B. You can see that you can see also in the change of value A and B. You can see we start A from 10, and you can see that A decreased significantly from 10 to 0 something. Right? But for B, you can see that B doesn't decrease much. It decreased very slowly. So it means that the learning rate for learning the value of parameter A and parameter B, it is different. Okay, that is why you will see, yes, in the next few slides, we will apply one technique called feature scaling. So usually we have to scale down the input features to so that it can be in a specific range. So we can just apply one learning rate and it will be good for all of the parameters in our model or our hypothesis. Okay.
លោកគ្រូសូមកន្លែងកន្លែង gradient A ទីម្ដងទីម៉េចលោកគ្រូ
កន្លែងណាក្នុងកូដ
បាទលោកគ្រូក្នុងកូដហ្នឹងបាទគុណគ្រូខ្ញុំគាត់ថាខ្ញុំឆ្ងល់ថាមូលហេតុវិញខ្ញុំរ៉ាន់ទៅខ្ញុំឃើញតម្លៃ A អាកន្លែង gradient ហ្នឹងលោកគ្រូរ៉ាន់ទៅខ្ញុំឃើញអត់មានឃើញដូចរបស់លោកគ្រូអាកន្លែង iteration ចាប់ពី iteration 1 ទៅបើខ្ញុំតម្លៃ A ចាប់កន្លែង iteration 1ទៅនៅតែ 9.6255 ដែរលោកគ្រូអត់បាន 6.2547 ទេ
ผมតែដល់ពេលណាមួយទៅវាធ្លាក់ចុះដល់នេះ
បាទលោកគ្រូនៅសក់លើខ្ទង់8ជាង iteration ទី80អីគ្រូ
Okay, so no, chẳng được chọn đây thế. So yes. So now any question? Any other questions?
លោកគ្រូជួយបញ្យល់អាកន្លែង evaluation របស់វាថាអាហ្នឹងវាបន្តិចគ្រូមិនឆ្លាតតន់
អានេះអត់ទេ evaluation នេះខ្ញុំគ្រាន់តែ print សាកល្បង print អា value ដែល predict ចេញមកពី model របស់យើងហើយនឹងអា real output ព្រោះយើងចង់ឲ្យអាពីរហ្នឹងស្រដៀងគ្នាទៅចានេះយើងមាន10 example យើង print មកអានេះ predicted ថានេះ real ហើយយើង observe មើលទៅយើងឃើញថានេះបើសិនជាតម្លៃអានេះកាន់តែធំអានេះគឺកាន់តែធំដែរអញ្ចឹងវាបានវាអាច learn បានហើយគ្រាន់តែថាវាអត់សូវ very similar ថ្ងៃនេះ7នេះដល់ទៅ24
អូបាទអញ្ចឹងបើសិនជាធ្វើមិនដើម្បីវា good perform គ្រូ
ហ្នឹងហើយដោយសារកន្លែងនេះយើងឃើញថា you can see here that B it will decrease, right? Actually it can still decrease, so you can train a lot more iterations so that the value of B will change to the optimal location as well. So for example, right here, let's try to train like 10,000 iterations. Okay, and here instead of print every iterations, let's say that I will print every in every 100 iteration. And I'll run again. Okay, 10,000 still not enough because the learning rate for B is too small, I think. Let's try 1 million and I'll print every 1,000. Okay, so this is 1 million, 1 million iterations, right? And then let's try to find this out again. You can see that the result is like much better. What we can do also in order to improve this is to use different learning rate for the two parameters. So for example, like A, it is okay for A. But for B, maybe I can, okay, so let's say alpha A is equal to something like this. And for alpha B, I will choose something bigger, so maybe 0.1. And when we update the parameter, we can use alpha A and alpha B, so different learning rate. Okay, so here I will try with just 1000 iterations, and I will print out once every 10 iterations. Okay. Okay, so here is our result. So A is equal to 1 and B is equal to around -2. So let's try to run the result again. So you can see the result now is very good. Like the predicted output is very, very similar to the real output. Okay. Question?
Lúc cô chăm chui send code ក្នុងឆានលោកគ្រូ
Yeah, okay, yeah. So, but in practice, it is not recommended to use different alpha, different learning rate for each parameter. Because here, like our linear regression model is very simple. We have only 2 parameters. But the real linear regression may have like 100 parameters. So if you use like one learning rate for each parameter, you have to use a lot of hyperparameters. So it is not a good practice to do that. That is why we have to apply other techniques in order to be able to use only one learning rate for all of the parameters. And that technique is called feature scaling, and you will see in the soon in our lesson about feature scaling. Okay, so I can share this to Microsoft Teams. Okay, Google Colab for exercise 4.1. All right, yeah, I have shared to Microsoft Teams. And also one more thing, you can see that for this code in particular, we use like the pure Python, and it is not very good as well in practice. When we have a lot of data and when we have a lot of input features, it is better to use a framework or maybe a library in order to help with this. You can see that we use a lot of loop. Especially we have, in order to compute gradient, in order to compute the cost function, we have to use a loop. And we have to loop through all of the examples in our data set. Imagine that we have like 1 million examples in our data set. We have to like do the loop with 1 million iterations as well. So it will be very slow and it is not a good practice at all. So in the next exercise, we will use other implementation technique like Python libraries such as NumPy, or for machine learning we can all use like a very for the deep learning tool, the deep learning library as well, such as TensorFlow and PyTorch. Okay, so we will see that how we can use those libraries in order to implement a linear regression model. Okay, yeah. Okay, so next we will talk about linear regression with multiple variables. So you can see here in this example, we have only one input. But for linear regression, we can have multiple inputs, not just one. Let's look at the same example about the land price prediction. But this time we have two inputs. We have in order to predict the price, we have to look at the size of the land as well as the distance from the city center. So we have two input features. So like each input, we call it features instead. So let's look at our notation. We have n. N is the number of input features. So for this example, we have 2. N is equal to 2. And you can see we have now the subscript. The subscript to represent which input feature that we are talking about. So you can see here. We can also, because we have 2 input features here, we can also write h as a vector instead of just a single value. So h is composed of x1 and x2. Okay, yeah. And for our hypothesis, we just have to change a little bit. So now we have 3 parameters, A, H1, B, H2, and C. What is this equation? It represents which, what does it represent? សមីការនេះសមីការអីគេយើងដឹង
សមីការ derivative ទីមែនទេ
ដូចអាមុននោះសមីការហ្នឹងគឺសមីការឡាយសមីការបន្ទាប់សមីការនេះសមីការគេដែលមានពីរអាញាប់ចឹង
ដូចខ្សែកោងគ្រូ Not sure about the detail.
No, we have 2 variables, but the degree is just 1. So here it is the plane. It represents a plane. So linear regression for the data that have that has 2 inputs, it is a plane. Because when we draw a graph to represent this one, it is something like this instead. Nice. It is like, so here we have okay, so let's say this one is x1 and this one is x2. So our data can be everywhere in the 3D space, right? So the linear regression is the plane. Okay, so I can draw something like the plane. Instead of just a line, it is a plane. Okay. Yeah. So we have 3 parameters now, A, B, and C. So yes, for two input features, 3 input features, 4, 5, 6, 7, 100 input features, we can write something similar. So we can use different name for our parameters. So here we use theta instead. So we call it theta 0, theta 1, theta 2 instead of just ABC. And you can see here the bias here, C, we represent it with theta 0. So that it is easy to read. And for each input features, the coefficient is the parameters with the same subscript. Okay. So if we have a 3 input feature, our hypothesis for linear regression should be theta 0 plus theta 1 h1, theta 2 h2, and plus theta 3 h3. Okay, so we can just continue to write our hypothesis like this. Or we can write it in a compact form. So j from 0 to n, theta j hj. And here's the number of input features in our for our hypothesis. And here you can see that we have theta 0, h0. You can see that theta 0, we don't have any, it is a bias. So we don't have to multiply with any feature. So here we represent h0 to be equal to 1, right? I think you can say something like theta 0, h0. If h0 is equal to 1, it is the same thing, right? Yeah. So this is our the general hypothesis for linear regression. Yeah. And in order to compute the cost function, this is the same thing. We can just compute the difference. So right now, it is not the difference between single value. It is a difference between vector. Okay. Oh no, not vector. Sorry, it is the same thing because right here, our hypothesis, it will produce only one single value. Yeah. So yeah. So the cost function is exactly the same. It doesn't change at all. Okay. And also for our gradient descent, we have to compute the gradient for each of the parameters. You see, we have to compute the gradient for all of the parameters, and then we update all of the parameters. But here you can see that here do this for all j, okay, for all parameters. But here we cannot do it alternatively. What I mean is that we have to compute all of the gradient first before we can update the parameters, right? Like in this with two input features, we have to compute gradient of theta 0, and then compute the gradient of theta 1, and then compute the gradient of theta 2. After we compute all of the gradients, we can update. Okay, and then update theta 0, update theta 1, and update theta 2. What we cannot do is that we cannot like compute gradient of theta 0 and then update theta 0. No, we cannot do something like this. We have to compute all of the gradient first before we update. Because if we update theta 0 right here, it will affect the computation of gradient of theta 1 as well. So we do not want that. We want to use the old value of our parameters in order to compute all of the gradients first before we update the parameters. Okay, so I think it is 3 p.m. now, so I think it is time. We can continue tomorrow, but yes, before we stop this session, any final question, especially about gradient descent and about linear regression in general.
លោកគ្រូខ្ញុំសូមសួរមួយលោកគ្រូអាកន្លែង code នេះឧទាហរណ៍តែខ្ញុំចង់ implement អាកន្លែង line linear regression ជាមួយ with multiple variable ហ្នឹងយើងគ្រាន់តែថាយើងគ្រាន់តែកែកន្លែង cost function ទៅប៉ុណ្្នឹងឯងចា៎
Yes ហ្នឹងហើយយើងគ្រាន់តែដូរកន្លែង hypothesis មកដាក់ឲ្យមាន3 parameter មកហើយអានោះបើសិនជាយើងមាន2 input feature ដាក់មាន3 parameter មកហើយហ្នឹងហើយត្រូវ update បន្តិច update កន្លែង hyper parameter hypothesis update និយាយទៅ update គ្រប់ function cost function ក៏យើងត្រូវno ដូចជា cost function ដូចអត់ចាំបាច់ដូរទេ
អញ្ចឹងយើងដូរតា
depends ទៅលើហ្នឹងហើយ
បាទអញ្ចឹងមានថាយើងធ្វើតែកន្លែង hypo មួយប៉ុណ្ណឹងឯងលោកគ្រូ
ហ្នឹងហើយនឹង gradient ពេលដែលយើង compute gradient វាត្រូវដូរដែរយើងត្រូវប្រើរូបមន្តហើយប្រើរូបមន្តនេះវិញ Okay អញ្ចឹងពេលដែលយើង compute gradient បើសិនជាយើងមាន2 input ជិតៗយើងត្រូវមាន3 parameter អញ្ចឹងយើងត្រូវកណនា3 gradient 3ផ្សេងគ្នាដែរ Okay, so you can try by yourself in the meantime. And tomorrow we will continue to feature scaling. What I mentioned before, the way that we can use so that we can, we can use only one learning rate for all of the parameters. So it is a good practice to apply feature scaling for all of the input features. Yeah, and tomorrow we will get into classification. Okay, so for now we just cover the linear regression, which is not what we want to use for text classification. But I want to yes introduce you to linear regression first before we get into the classification part. All right, yeah. So yes, tomorrow hopefully we can finish the classification part as well.
គ្រូសំសួរទៀតគ្រូសំសួរមកខ្ញុំសំសួរចំពោះpackage ដែលយើងអាចប្រើជា TensorFlow អញ្ចឹងវា support Python 3.10 ឯងគ្រូ
យើងមើលកន្លែង download របស់វាតើវា support ដល់ប្រហែល
វាឃើញតែ 3.9
ដូចជា 3.10 ដូចជាថ្មីពេកដូចវាអត់ទាន់ប៉ុន្តែក៏វាមិនជាហើយពេលដែលយើង install PyTorch install TensorFlow មើលទៅ install PyTorch យើងដូចជាឲ្យយើង select យកតែយើងរើសយក Python ដូចជា Python version ប្រហែល
វាអត់មាននិយាយបងវាដាក់ត្រឹមតែ 3.5 ដល់ 3.9
ហ្នឹងអញ្ចឹងយើងប្រើ 3.9
ពួកខ្ញុំមាន Python 3.10 ខ្ញុំ
សាក install សិនទៅវាដូចជាមិនគួរព្រោះ 3.9 3.10 ហ្នឹងក៏វាមិនខុសគ្នាប្រហែលដែរកុំឲ្យតា version 2 និង version 3ហ្នឹងបានវាខុសគ្នាខ្លាំង
បាទ
but for our lesson we will use PyTorch. So if you can install because in Google Colab we already have PyTorch, so TensorFlow as well. But personally, I am more familiar with PyTorch, so we will use PyTorch in our exercise.
Thank you, teacher.
Okay. ហ្នឹងហើយមិញណាគេមានសំណួរអីមួយទៀតមិញដូចមានណាគេចង់សួរអី No
លោកគ្រូក្នុងហ្នឹងបើសិនជា Python 10 3.10 គឺវា support ជាមួយនឹង TensorFlow ឬវា support តែ 3.9 ហ្មងគ្រូខ្ញុំធ្លាប់សាកកាលពីខែ
អូខេអញ្ចឹងអត់មានជំរឿនមានតែប្រើអញ្ចឹងប្រើ Google Colab នេះទៅមានក្នុង exercise យើងគ្រាន់តែបន្តិចហ្នឹងអត់ចាំបាច់ត្រូវការវាអត់ត្រូវការ training capacity ខ្ពស់ computing capacity ខ្ពស់ណាពេកទេសម្រាប់ lesson យើងប្រើតាម Google Colab ទៅអញ្ចឹង
បាទអរគុណលោកគ្រូ
Okay, so yes, I think we can stop now because it is time. So see you again tomorrow.
Goodbye, teacher.
That's goodbye.
Really cool.